Let us look at Coset decomposition. Basically, we take a group, take a subgroup, and using the subgroup, we arrive at all the left cosets or all the right cosets. In the process, breaking up the group into cosets which are of the same size and the elements in them are not repeating. Okay, let's see what we mean by that. Given a group G under an operation star, let H be a subgroup of G. Now we will consider only the left cosets first. And the same thing would apply for right cosets as well. So consider left cosets. We have seen previously in the properties of cosets that G, that is a group, is nothing but the union of all the left cosets. So H is a left coset because E is the identity and E times H equal to H for all H in the subgroup H. So we now have one coset, that is H, the subgroup itself. Now if A is in G but not in H, then AH, or rather A times H, is a left coset. And since A is in A times H but not in H, we have two distinct left cosets. That is H, what we found in the previous step, and A times H. Let's take another element which is in G but not in H. And B is also not in the coset A times H. So it is not in either one of these. Then B times H is another distinct left coset. So that now we have three left cosets. That is H, A times H, and B times H. If C is in G and C is in H or in any other cosets that we have already found, then C times H is not a distinct left coset. So we still have only three left cosets. Let's take another element. So if D is in G but not in H, and it is not in A times H, and it is not in B times H, then D times H is another distinct left coset. So now we have four left cosets. So H, A times H, B times H, and D times H. In this way, we can identify all the distinct left cosets or class of left cosets, which in turn maps to partitioning of the group G. Okay, now let's take an example and work through it. So let's take this permutation group under the operation composition. We have already seen this. Remember the Cayley's table of this? So let's take the subgroup E, permutation 1, 2, where H is a subgroup of G. So elements that are in G but not in H are what? Just follow through. E is there in H, so we ignore it. Permutation 1, 2 is there in the subgroup, so we ignore it. So the remaining will be the elements which are in G but not in H. So let's start finding the left cosets. So E times H is equal to H. So that is our first left coset. That is E, permutation 1, 2. Let's take A is equal to permutation 1, 3. Then 1, 3 times H is equal to 1, 3 times E. 1, 3 times 1, 2. Now 1, 3 times E is 1, 3. You can refer to this Cayley's table if you want. 1 3 times 1 2 is 1 3 times 1 2 is 1 2 3. So permutation 1 3 and 1 2 3 is the second left coset. Now let's take 2 3. So 2 3 times E and 2 3 times 1 2. So 2 3 times E is 2 3 and 2 3 times 1 2. 2 3 times 1 2 is 1 3 2. So that is our third left coset. Now do we need to go forward or continue in this process using 1 2 3 and 1 3 2? No. Why? Because remember the condition says what? If C is in G and C is in H or in any other cosets, then C times H is not a distinct left coset. So here if you notice, if we take 1 2 3, it is already there in this second left coset, and 1 3 2 is already there in the third left coset. So 1 2 3 is already there in 13 times H, and 1 3 2 is already there in 23 times H. So we have partitioned G into three left cosets. One is the H itself, the subgroup itself. Then we have permutation 1 3 and 1 2 3, and the third coset is 2 3 comma 1 3 2. Similarly, set of right cosets are H comma 1 3 comma 1 3 2 comma 2 3 comma 1 2 3. So just to make sure you are clear about this, this is a set of sets. So overall set is the set of cosets, left cosets, and each one of this is a particular coset. Here if you notice, left cosets are not equal to right cosets. Yes, the subgroup itself is there in both left and right cosets, but here you see we have 1 3 and 1 2 3, and here we have 1 3 and 1 3 2. Here we have 2 3 1 3 2, and here we have 2 3 1 2 3. So the left and right cosets are not equal. So what does that tell us? It tells us that the subgroup H is not a normal subgroup of G. And the way we write it is H is not a normal subgroup of G. So instead of having a less than or equal to, we have a triangle facing to the left and equal to. And since it is not, we are striking it out. So H is not a normal subgroup of G. Now, if left cosets are equal to right cosets, maybe in some other example, then we would say that H is a normal subgroup of G. And in that case, we would say H without this slash, just the left-sided triangle and equal to G. So when we say partitioning of the group, we basically mean dividing this set into, in this case, 3 blocks of equal size. H, remember, contains 2 elements, E and 1 2. Here you have 2 elements. Here you have 2 elements. So we have equal partitions, or partitions containing equal number of elements. And very importantly, that the elements themselves are there in only one of these cosets or partitions. Here we can also verify this statement that the group itself is a union of all the cosets. So let's take the 3 left cosets. We have H, which contains E and 1 2, 1 3 and 1 2 3, 2 3 and 1 3 2. So if we take the union of these 3, cosets, left cosets, we end up with the entire group. And the intersection of these two cosets or these two cosets or these two cosets, or in other words, intersection of any two left cosets will be a null set. That means no elements will be there in more than one of the cosets. Interesting, right? That was coset decomposition. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.